Hello there, students. Welcome back. All right. I really want to make sure that you guys understand this difference between initial condition problems and boundary condition problems, and how one relates to what we're doing with regard to weather forecasting, and how the other one relates to what we're doing with regard to climate forecasting. And in order to show you, I want to show you another example of a kind of system that we could be creating a numerical model of. Previously, we've been talking about numerical models of climate. How about a numerical model of a roulette wheel and playing roulette? I mean, the roulette wheel and the roulette ball together make a system that is something that probably we could make forecasts of, and we could simulate using a numerical model. Do you know how to play roulette? Let me show you here. First off, never play roulette. It's one of the worst games at a casino, as far as like the odds and so on. But there's a guy who's running the roulette wheel. He's called the dealer, confusingly, even though there's no dealing involved. And the dealer keeps the ball going, the wheel going all the time in one direction. And there are on the roulette wheel a large number, I think it's 40, maybe it's 38, little pockets is the right word, where the ball can stop when they spin the ball in here. And you place your bet on either an individual single number bet, like it's going to come up 16, or you can bet on a color like red, or you can bet on the top dozen or the bottom dozen, and so on. All of them are losing bets, by the way. So the dealer gives the wheel a spin, and people put their chips out onto the mat, and they make their bets. And at some point, the dealer takes the ball and gives it a little spin in the opposite direction. At some point, the little ball is going to start bouncing around, and it comes up, lands on one of the pockets. In this case, it landed on black 28. And so somebody who bet on black 28 now wins at 35-1 odds, usually. And it's a fairly simple game. I mean, it's just physics, right? The wheel is just spinning. We know the physical laws that control things like the spin. There's a lot of pieces to this here. There's bearings and so on that are determining how the wheel is spinning and how fast it's spinning and how much it's slowing down. But you know what? It's just physics. And the ball is just a ball. It's just a sphere. The Nevada Gaming Commission has very specific guidelines as to how the ball is made of and the mass of the ball and how smooth the ball is and all that kind of stuff. And when you put the ball into the table is, the wheel itself is coated with materials and so on that have very specific properties with regard to their friction and so on. At some point, the ball hits these little metal nubs here called pins. A lot of times people call those diamonds. And bounces off of them and then begins to bounce down here in the middle of the wheel until it comes to rest in one of the pockets. It's all just physics. It is all stuff that folks like Isaac Newton discovered, like, centuries ago. It seems like something that we should be able to create a numerical model that is able to simulate. I mean, it seems like once the wheel is spinning and once the ball is in motion, it's all just physics. It's all just very simple. Take physics to 11, and you'll learn about the motion of a ball and friction and the rotating motion of the wheel itself and so on. It seems like we should be able to make very good simulations of what the wheel is doing. In fact, it's been tried. Back in the 1970s, a group of technology nerds decided that they were going to do that, and a book was written about their adventure called the Eudaimonic Pie. Eudaimonic is a complicated word that means something like lucky. And the folks behind the Eudaimonic Pie had this idea that they were going to beat Vegas by using a computer to actually run a numerical model of the roulette wheel. Now, they actually hid the computer in their shoe. Keep in mind, this is like 1979 that this was going on. So it was a very primitive little computer compared to, say, your cell phone or something like that. But they had this idea that they should be able to beat Vegas. What they wanted to do, when the dealer spins the wheel, there's usually a few seconds before he drops in the ball. And what they wanted to do was they wanted to know how fast the wheel was spinning. Well, it's actually not so hard to see how fast the wheel is spinning. There's all these 4 little posts on here, and there's 2 brightly colored, the 0 and the 00 are on here. And so what they did in that was chronicled in the Eudaimonic Pie was they had a little key inside of their shoe here, and they would tap when the little peg went by, and after a couple rotations of it, the little computer in their shoe had a pretty good idea of how fast the wheel is spinning. And, once the wheel is spinning, it's just physics as to how fast it's spinning, and at you could easily numerically model how, at any given microsecond, exactly where the wheel is. Similarly, when it comes time for the dealer to put the ball in, the dealer puts the ball in and the ball starts spinning, but the table is still open. You can still place your bets for a few seconds, maybe 20 seconds more. The casinos like to leave the table open for a few seconds there because people start feeling lucky. They got a good feeling it's going to come up red or something like that, and so they leave the table open. So the dealer spins the ball here, but the table's still open. The guys behind the eudaimonic pie had the idea that while the ball is spinning, they would key in with their toe how fast the ball was spinning. They would time as the ball went past a particular pin or something like that. And okay, after the ball went around 2 or 3 times, the computer has a pretty good idea of how fast the ball is going. And once the ball is in motion, no one touches it. And after a few seconds of the ball being in motion and the wheel spinning, the dealer closes the table, no more bets, and physics plays out and it comes up black 15. The people behind eudaimonic pie said, we're going to beat Vegas here, because with this computer hidden in their shoe in like 1979 or whenever the book was, the events of the book happened, they thought they were going to be able to numerically simulate with a little computer chip in their shoe how this was going to work. Now, that didn't go very well. They had all kinds of technical problems and so on, and eventually the casinos caught on to what they were trying to do, and I don't think anybody's fingers got broken, but it wasn't such a good thing. It's part of the reason why now most casinos only give you a few seconds once the ball is in motion. They don't want anyone trying anything like that. But you can imagine nowadays with your cell phone, we could make something like this work. I mean, we could run a numerical model of the roulette wheel on your phone, and it wouldn't be all that hard to picture where, you could get an app, and when the wheel is spinning, you could watch one of the little posts go by, and you could tap, 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 and get an idea of how fast the wheel is going. Like if you tapped on the phone every time the peg went by or something, and you could do the same thing. That was a terrible spin there. You could do the same thing with the ball, and then the phone could tell you which, could run a numerical model and tell you, based on the physics, the equations that describe where the ball is and how the wheel is spinning, it's going to land in the pocket 30 red. And you'd win 35-1. It's not hard to imagine that it could be done, but it doesn't work. In fact, I checked. At least in the Android marketplace, there are no apps that do this. There's all these apps for cheating at roulette, but they're like guessing lucky numbers for you and stuff. They don't actually have anything to do with the physics of the situation. The guys behind the eudaimonic pie tried this, and they could, even in a lab, they had a roulette wheel in the lab, and they were trying it, without bright lights and drinks and pit bosses and stuff in a Vegas casino, and they couldn't get it to work. And they realized that the problem was maybe a little too complicated. They were literally trying to decide it's going to land in 27, or it's going to land in 31, or something like that. Later they said, you know what, you don't have to get exactly the right number. It was good enough to know, the ball will end up on the same side of the wheel as, the single zero, or it'll end up on the same side of the wheel as, the double zero, and yes, any given bet you wouldn't probably win, but you'd win more often than you would otherwise, and you'd actually end up money ahead. And it'll also be less suspicious and less likely you get your fingers broken by a big security guy. And it all seems like it really ought to have worked. So why doesn't it work? Turns out you can't even play the game the way they were trying to do it in eudaimonic pie, where you were just trying to guess which half of the roulette wheel the ball will end up on. But it turns out that the equations behind what's going on here on the roulette wheel are not in your favor. It's a system of equations that describes the position of the ball and the position of the wheel. It happens to be a system of differential equations, but they're initial value problems, initial condition problems. In order for this numerical model that simulates where the ball is going to end up on the wheel to work, you have to have very, very good information about where the ball started out, how fast the ball is going, where the wheel started out, where the how fast the wheel is going, etc. And you don't have that good of information just tapping on your cell phone, or those eudaimonic pie guys just tapping on a key in their shoe. In fact, even in a lab where they could measure it with more precise equipment, they couldn't measure the speed and position of the ball accurately enough to make this work. They couldn't measure the speed and the position of the wheel accurately enough to make this work. Why? Well, you know what? If the game were simpler, and let's say the game was not to figure out where the ball was going to stop. Let's say the game is to figure out which of the 6 pins around the outside of the wheel the ball hits first. Well, that's a game you probably could win. If the game was actually figure out which of those 6 pins you were going to hit, the physics are not so bad. But once the ball hits a pin, things go crazy fast. Because the very, very precise angle at which it hits this pin changes the way it bounces off of the pin radically. If the ball hits the pin one way, it'll head off into a different direction. If the ball hits the pin even at a tiny, tiny bit different angle, the ball bounces in a different direction, and suddenly your prediction is terrible. And you don't know the position and speed of the ball well enough to know exactly how it's going to hit that pin. And since you can't, yes, you might be able to predict that this is the pin it's going to hit, but once this has happened where it hits the pin, your knowledge of the initial conditions aren't good enough to figure out which way it's going to bounce. So it's going to bounce in a totally new and unpredictable way, and now your predictions are useless. Now you don't even have the right way the ball is bouncing or where it is on the board and on the wheel, and your forecasts are no good at all. Similarly, the same thing happens, the little divisions between each of these pockets are called frets. And if you get a good spin going here, let's see if I can do it. Again, once the ball starts bouncing around on those frets, every one of those little bounces would require a very, very precise measurement of where the ball is at any given time. And you just don't have that. It's an initial value problem when you're playing this game. When you're playing the game of roulette, you don't have good enough information about how the ball left that dealer's hand and how the wheel was spinning at the beginning for your equations to give you the right answer. Yes, if you had infinitely good information about how fast the ball was spinning and how fast the wheel was spinning and how hard he threw it and so on, yes, you could do it. But we don't have infinitely good information. So we are not able to make a good numerical model of where the ball will end up because we don't have that good of information about the initial conditions. That's why it's a game. In the same way, weather is an initial value problem or initial condition problem. The 7 primitive equations that describe how the atmosphere changes over the course of time are an initial condition problem. You would have to have infinitely good information about the current conditions of the weather, like exactly to many decimal places the temperature and the pressure and the winds and so on, for the equations to be able to make a prediction well into the future. Yes, much like in the game of roulette, yeah, for the first few seconds I can make a pretty good prediction as to where the ball is going to be. But with time the forecasts get worse and worse because I didn't have a very good initial conditions for the ball. In the same way, my forecast for the weather using a numerical weather prediction model starts off not terrible, but as the days tick by in the model forecast, the forecast gets worse and worse because we just didn't have that good of a knowledge of the initial conditions. So I wonder if there would be a way that we could change the rules of the game of roulette so that we could make it something more predictable, something that we could use as a boundary condition problem rather than an initial condition problem. Let's change the rules. Let's say that instead of the way we've been playing it now, let's say that the game is a little bit rigged in the sense that there's a giant magnet under the 00. Okay? Now, in practice, the ball is actually made of glass. It's not made out of metal. Let's say it's an iron ball, okay? Alright, does that change the rules of the game? Well, it's how the game is played. Well, now, in addition to the basic physics of like the ball bouncing off the pins and things like that, there's also an external force of this magnet pulling the ball toward 00. Doesn't necessarily mean that every time I spin the ball it's going to end up on 00, but like if I get close to the 00, maybe the magnet will pull it in. That certainly changes the rules, and this external condition, this boundary condition, to use the term from differential equation, makes the game a little bit more predictable. I could probably, if my numerical model knew that that was part of the rules of the game, could actually make a much better forecast. We can even take this to an extreme here. What if we change the rules altogether? Let's say I don't really care which of these pockets the ball ends up on. Rather, what I want you to to try to figure out is where will the ball end up? Will it end up down here in pockets, or will it end up balanced on one of these pins? Now, if you want to play that game and bet that the ball will balance on a pin instead, you have a gambling problem. Although I suspect Vegas would be willing to write you that bet, to cover that bet. Okay, this would be a different type of game. And you'd still have to know the physics of how the wheel is spinning, and you'd still have to know the physics of how the ball moves and so on. But the truth of the matter is the initial condition isn't so important right now, right? I mean, I could do all that math and find out, hey, the ball ended up down in pockets instead of down balanced on the edge of a pin. Heavens, I'll spin the ball even the wrong way this time. And I can do all the math. It's still a very complicated problem to determine, but you know what? The ball ends up at a pocket instead of on the pin here. Why? Because of gravity. Because gravity, this external force, this acting from outside the boundaries of the roulette ball system, is pulling the ball down toward the pockets rather than balancing it on the edge of the pin. And you know what? The odds of it stopping on the pin probably would be different if, like, for example, we were playing the game on the International Space Station under zero gravity instead, right? Or, yeah, just under different conditions like that, we might be able to make the game different. But as long as we knew the basics of things like we're playing the game someplace with gravity, this different way of playing the game would be a whole lot more predictable. The longest spin I've ever seen. Anyway, in the same way, when we're making predictions about climate, I'm not caring that in particular, on July 1st, 2110, that the high temperature in Omaha is going to be such and such. I don't care about that. That's an initial value problem. I couldn't possibly make a forecast of what the weather's going to be like on July 1st, 2110. On the other hand, that's not really what I want for my answer anyway. I'm changing this to a boundary condition problem. Instead of knowing what the weather's like that particular day, what I want to know is, like, what is the weather like in the decade of the 2010s, of the 2010s, okay? Where, like, yes, some days it'll be warmer, some days it's cooler, but overall, what is it like? And that's going to depend on external problems that are properties that are external to the 7 primitive equations. Stuff like how much greenhouse gases are in the atmosphere, or the amount of aerosols and dust and stuff in the atmosphere. Stuff that's external to the 7 primitive equations. And stuff that we have a better handle on. So we can actually make a pretty good forecast well in advance of the climate, because the climate prediction is a boundary condition problem. In much the same way I can make a pretty good forecast in advance of where the ball is going to end up. It's going to end up in a pocket. If I'm demanding that I have to know which pocket, that we have a problem. But if I want to know more broadly, just does the ball end up down here, or does it get thrown off the table, or does it end up on a pin, we can figure that out without such detailed understanding of the initial conditions. So that's pretty cool stuff, isn't it? It's kind of neat to think about how there's different ways, different physical systems can be modeled using differential equations without even having to take a 500 level math class. You can understand what's going on. Now let's actually ask 2 more questions as we wrap up this lecture. For question 9, this game of roulette is based on simple physical laws, much like the atmosphere is, but it's hard to predict or model where the ball is going to end up in roulette because the physics of roulette are a very sensitive blank condition problem. Are they an example of an initial condition problem or a boundary condition problem? I don't think that'll be too hard after watching that lecture. Alright, choose one of the 2 links below this video and get a little feedback before you move on to the 10th and final question.